Okay, so it's a GAN, or I think it's GAN or GANs. It's okay. So generative adversarial networks. So this one is I can say it's kind of totally different from the network that we've been studied in this. So let's see what kind of the idea that we have that this guy has. This one, you don't worry about it. It's and these two are the materials that there's a link. So if you want to have, like, if you guys want to study more in details, probably that would be the website that you guys can go and find out more like materials. And all the materials that I have is based on these two or three. So I think you already know we have supervised and unsupervised. Supervised. And the difference is that this one we should have input and outputs. And on the other hand, unsupervised, no outputs. So for the supervised learning, say, like regressions and the classifications, whatever, trying to figure it out, this the relationship. From the training data set, we're gonna have pair in the input and outputs. In the unsupervised, we don't have any outputs. Okay, so that's for supervised learnings. And the first thing is discriminative models. What I mean by that, this is suppose we have some kind of discriminative models, then I'm gonna explain everything with the images and the pictures. So, and here, say you have the image of man or image of women, like male and females, and see if take this one as an inputs, probably if that's the classification problems, classify that with this inputs. We're gonna say the network's gonna say supposed to say it's women. It's a classification problems. So in general, discriminator models learn how to classify the input to its class or labels or outputs, whatever. That's discriminative. And let me move to the generative models. Generative model means, okay, say, hey, what kind of, so any kind of AI models and CNN, whatever. Now everybody's kind of take it for granted or understand this, the classification, performance, or accuracy is like as good as humans. That's okay. But now we're gonna ask different tasks to AI. So, okay, hey AI, like now we know that you guys are good at classifying them to make it distinguishable, but this task is a little different. I want to ask you to draw the picture of whatever you think it's a man, like. So I want ask AI to generate. So this is totally different task. This one is classification problems. This one is somehow we're gonna ask AI to produce from nothing or generate something that you believe this is the male or females, whatever. Then I'm gonna ask you, which task do you think is more difficult, generative or discriminative models? Which task?
Generative.
For this case, actually AI doesn't have to fully understand what makes man, what kind of image makes the man, or what kind of image make like the woman. So they have to fully understand to classify them. But on the other hand, in order to draw or make or produce, generate the picture of man or picture of women, the AI has to totally understand, right? Otherwise, we cannot produce. So it's a generative models, generative. So starting from here, because here the idea is from autoencoder. Here is decoding part and is encoding part. So just from latent space, here is it's reconstructed. So this one you can think of as one of the type of generative models. From latent space back to reconstruct back to the original space. Okay. Here it's in here we see latent space or latent code or random factors. Say suppose we have suppose it in three-dimensional latent space, then we need 3 neurons or units, and each neuron, say we has random variables with say either uniform distribution or Gaussian distributions. So this guy will generate some random numbers, and through the generative models, say here is 64, and colors have 3. So we have to generate it, reconstruct the original image. And here, I don't know, maybe like we need at least, I don't know, 100 or 200 latent space or variables or latent code that we need. That's the idea of generative models. Now, over here, generative models and on the distribution of training data set, I want to explain what the distribution of training model means. So let's go back to, let's talk about the probability first. And here there's, let's say, the probability, all right, let's stick models. Model distributions and data distributions. Probability distribution means, I mean, the simplest, I think this always when you study or learn the probability theory, this will be the first one. Says that we have many dice and will be random variables and assign it the probabilities. So in here we have from 1 to 6. There's 6 different discrete case. Or sometimes we can have continuous as well. We call it as random variables, and we assigned each random variable. We assign some number, which is probabilities, and all of them are positive, and the summations equal to 1. That's the only constraints that we, in order to define what the probability is. So that's the probabilities. In that case, so we call it probability density distribution, density functions, or probability mass functions. If that's a discrete mass, it's continuous, then we call it density. That's something that you're supposed to learn from the probability theory. Then let's see. What if the X is actual image in the training data set? So now it's X is image. Then X can be represented as like this. So that's the complexity of the X. That's the dimension of X. So you have 64, 64, and RGB, right? So that's the dimension of X. Then each pixels, right? Then have, say, from 0 to 1, is you can have like 0 to 2, or you can normalize it, so you can have value from 0 to 1. Each pixel has that. So these each will be like random variables. And we have this number of random variables, so we call it random vectors. That's the dimension of our X. And each X, each pixels have some kind of, let's say here, say, I don't know, like 121st, the pixel, the value is, this one value should be like from 0 to 1. And we might have some, like, I don't know, maybe it has some kind of distributions like that. So let's see, there is probability density function for the data that represent the distribution of actual image. So say this is the X, and this is the actual probability distribution of the X. Of course, this one is like in 1D or 2D, but in real values, it's extremely high dimensional space, even we are not able to visualize or able to draw. But this is kind of the simplest image that you're gonna use to get some insight or intuitions. And here is the idea is that we have data this is true, because data is data, right? So we assume that this data is actual values and true process or true something. Then in this one we'll have some kind of probabilities. And in order to generate something from models, I didn't define what the model is yet, but if we have P model of X, if we are able to make these things similar, that means these two, that's the probability are pretty much like this. Then if some values here and generate it from these models, it's gonna be pretty much the same as the actual data set. That's the idea of generative models. So the goal of generative model is to find this guy that approximate this. This one is, again, is assume that this data is the answer, the true values. This is something that we need to update it to approximate to true probability density functions. Does that, I mean, okay, so it's this kind of the abstract way that I can explain for generative models. In the following slide, probably it's much like, I think it's gonna be easier to understand. Then we're gonna use the deep learnings or neural net to make that one, right? So let me see. So again, over here it's latent space. See, the simplest matter is, say, suppose we have 1 neurons, and this guy, we're gonna assume that it's Gaussian. We're going to assume this its latent space is Gaussian, but in output, this one, it will be the P models of X, or in this case Z. It should be same as P data. So how do you get distributions from using neural net? This is the task. Now it's talking about the probability. So we want to make probability density functions using neural net. Okay, starting from either uniform distributions or Gaussian distribution, something that distributions are simple enough and you already know. Then we have over here, it's neural net, and let me move back. This one is, I think this is the most important slide that you have to understand for the generative model is neural net is a deterministic transformation. There's no uncertainties. There's no like stochastic behaviors. Deep learning is a deterministic. Okay. And say this is the input distribution. Say it looks like it's a Gaussian distributions. And suppose this one is the output distributions that we want. Say this is the output distributions that, and what neural net does using deterministic transformations from x to g of x, make transformations to get. So from this one, using like this some kind of mappings, I can make any kind of probability distributions. Okay, so what we want to do, suppose we have this one is P data, then this one is the latent code or space. Over here, neural net models. We want to find out these using like backpropagations or whatever. We learned the nonlinear mapping functions to get models. And we can generate any kind of approximated functions over there using these nonlinear mapping functions. So remember, the neural net does not generate distributions, but it maps non-distributions. We're gonna use uniform or Gaussian distribution to target distributions, basically this. So again, neural net is deterministic transformations, and neural net is not able to create or generate the distribution itself, but it's gonna do some kind of trying to figure out or try to find out the mappings so that it maps from non-distribution to target distributions. Does that make sense? Does that make sense? So what we wanted to, this one is that we want to establish or build, but in order to that, we need to know probability density functions of training data set that we have. training data set that we have. We should know this one in advance. And these are the same, but it's in high dimensional space. Again, in one dimensional, it will be the Gaussians. In two-dimensional space, it will be like in very shaped things. And generative models, you know that, it's a deterministic mappings. It will generate the distributions, and it will be the target distributions from the training data set. And I want to make these two almost identical or as close as. Once we confirm that these two distributions are pretty much the same, then once we're done, what I can do, I can just do random samples and do the 4 propagations. Say now this will be the generated the values from in the original space, and I can do any, like what we did in the autoencoder. Remember, is then I can do any values and it will be like, so that's how we do. And this is the same. And here is the for the generative models, we have to train the net that models the distributions, right? So in such as the target distributions over images. But the problem or the issue is that we don't know the target distributions from the data. We don't know, actually. We have to do a lot of samplings, and we have to make inference to compute the target distributions. Here is the big moment that the GAN idea is to kick in. So it does not work with the explicit density functions. So forget about it, and instead we're gonna make totally different approaches. In this case, it will be the game theoretic approach. What do you mean by this? And let's think about that. So the idea is that, so the idea is coming from Turing Test. One way to judge the quality of the models, the quality of the model means this means we're gonna do sample from models, and we can generate it, and we can sample from the data set. Okay, then we're gonna ask. So let's think about this. We have A is AI, and this is human. You guys have any questions so far? I mean, I'm using like probabilities, and I mean, it's good to know, but you don't have to understand. You don't have to like fully understand. You don't have to do it. But from now on, it's a key idea of GAN. So probably from now on, it's much easier to understand. Here is, like say you guys, the question is AI. I think the ultimate goal of AI is like act or thinking as humans, right? That will be the ultimate. And how can we tell, or how can judge that this AI is good or not? Then the Turing is one of the ideas. They say here is you have like war. So you guys are on the opposite side, so it's not able to see it. But you can ask, you can do Q&A. You're gonna make some questions, and either AI gonna answer all of your questions, or actually the human might answer for your questions. And you're gonna listen to what they say, but you don't know the answer is coming from AI or humans. If the performance AI is poor, is not good, then probably it's much from this side it's easier to tell, right? Okay, this answer is must be AI or must be humans. But if the AI is almost, then for this guy is not easy or really difficult to tell. Difficult to tell. That means the AI is this is like, right? The data is from over there is from the humans and the model is from AI. So we're gonna make the samples and we're gonna tell whether this is from the AI or this one is from humans, and if these two are like indistinguishable, like that means the AI is, I mean this good performance of AI, we can say that. So as a summary, model to produce the samples which are indistinguishable from the real data as judged by discriminator. We're gonna say this one is discriminator, whose job is to tell is real from fake. So that's the key idea of Turing test. In GAN networks, is we're just gonna take that, the idea that to just implement it. So the idea behind the GAN, actually we have two networks. The first one is generator, and the second thing is a discriminator. So what the generator does, this is the model that this is the model, generative models, trying to produce realistic looking samples. On the other hand, on the opposite side, for discriminator, trying to distinguish between real and the fake data. Fake data means is a generated data or samples from generator networks. So we have two networks are competing each other. It's like game theory, right? So generator model or generative model trying to fool the discriminator network. If the discriminator is not able to distinguish, that means the real data and it's almost, right? Then the fake data is realistic looking data. So it's fake, but it look like real data set. That's the key idea or background or fundamental philosophy of GAN. Okay, so I mean, generative model is not the first time that I introduced and that I showed. It's called, if you move back from before the midterm exam, the autoencoder was the first. So it's compress the data set and we do decodings. Over here is encodings. The latent space, we do decodings. So basically this one is same as generative models. So let's see so this one is generative models. So here is generator. From latent space, we're gonna generate something because its data is generated, and we're gonna add discriminator. It's gonna take the inputs, but it can take the inputs from generated one or real one. We don't know which one is that. So the job of discriminator, we have to tell is whether it's real data or fake data set. So we have two networks. If this one, if for discriminator, say in this case, oh, the data is coming from real. In this case, data is from generator. That means generators and the real data is look different, right? Then the generator is not doing good job on what they're supposed to do. And if the discriminator is, if that's the difficult to tell, that means the generated data is realistic looking, right? So let's think about intuitions. So we will have generator and discriminators. We have one over here is we have one discriminator, but we can take it can take the inputs from generator or real data set. That's why we have, looks like we have two, but say we have the real image, and from the latent space passing through generator. So this is image is a generated one, is a fake image. And we're gonna say in real, in the label is 1, and fake is zeros. So this is, then since it's this real one, the discriminator should say is 1, right? And for fake data, we take the fake data as inputs. This one should say zeros, which is a fake, right? So from the discriminative perspective, if we take the real data set, the value should be close to 1 because 1 is real. On here, if take the inputs for discriminator from the generator, should say zeros, close to zeros. But for generative models, from latent space, generative, these are generated fake image, right? And we're gonna feed that into discriminator. And from generator perspective, we want to pull the discriminator. So I think that discriminator should say it's 1, even though it's a fake. This one is not easy to understand, but this is the key moment. For you guys know what I'm talking? Because here for generator, we're gonna generate it, but trying to make generative images as real as possible so that we can pull the discriminator, say make it, it's gonna say it's a real image. So it's close to 1. Does it make sense? Okay.
Yes.
Okay. Now, I mean, this all the like theoretical backgrounds, I think I already covered it. Now, the next step is that how we can implement it in probably in neural net or deep learning, or in TensorFlow, so that they can understand. And we have to define the loss functions. Again, for discriminator, it's a classification problem. And we know that we use cross entropy, right? For classification, this is the equation for the loss functions, or the cross entropy. Or you can think of it as a classification problem, or you say it's binary classification problems. And it's a typical loss functions because it's a classification problem from 0 to 1. Okay. Now let's think about this one. D is the X is coming from real data, and now it's feed into discriminator. And this one should say for discriminator, let me see that. For let's think about the discriminator first. Discriminator, we want to maximize this, then there will be and d of x can have either from 0 to 1. So I want to maximize this one, it should be 1, right? And if this, for discriminator, if for starting from the latent space, this one is generated and fake one, and this one is trying to maximize it, right? So that means this one is to maximize it should be 0, right? Because to maximize it. So if that's in the generated or fake image, the discriminator should say 0. Make sense? So I mean, this is the way that we is implemented in as a loss functions. For discriminator, for x, we get 1. For z, it should be 0s because it's a fake one. Now, for generator, over here there's no g function, so it's independent. We can ignore it. Now, for generator, I want to minimize it. So to minimize this one, this value should be 0s. Then means it's 1. Right? So this is fake 1, but I want to say discriminator is thought as this one is thought as a real one. So it's MinMax problems. For discriminator, I want to maximize the loss functions, and for generator, I want it to minimize it. And this is kind of, and okay, this is the loss functions, and there's no issues on that. But as a side note, there's some minor issues. And let me see. Let me see. Over here. At the beginning of training the process, at the beginning of, if you, so this one is log 1 minus, say it's x. If you plot this, is when, and at the beginning is the gradient is relatively small, so it's I mean, we're gonna use a backpropagation as a gradient descent method. So if this gradient is relatively small, it's what is at the beginning, this learning process is gonna be very slow, right? So the idea is that instead of minimizing this one, I want to maximize this guy. Then if you plot this one, log of x, now it's, as you can see, the slope is pretty high. I mean, that's minor issues, but I mean, okay. So we're gonna use this one as a, so there's two steps. The first one is I'm gonna fix the generator. That means I will update it discriminator to minimize this one. And the next step is I want to fix discriminator and I want to optimize with respect to generator, like these functions. Okay. Maximize this guy, same as minimize minus of this guy. It's the same. So all of them are minimization problems. Now, what we need to do, the rest thing then is how to implement this, the idea of GAN in the syntax of TensorFlow.